So we're going to talk about FreeRTOS. So last lecture we were busy with the essential elements that make up a real-time operating system and how do you implement that from ground up. Now FreeRTOS is actually an open source real-time kernel scheduler that you can use, and it's actually used in industry as well. So again, the same story. It allows MCU applications be organized as a collection of independent computational threads. The kernel will decide which thread should be executed, looking at a priority assigned to each thread, assuming a single core MCU, so we can only execute one single thread at a time. So we assign priorities, high priorities, to those that should get high priority in executing. So we've talked about this quite a bunch of times. As an application designer, you're in charge of figuring out what those priority assignments should be. And in general, of course, that can help to ensure an application meeting its own deadlines. So in FreeRTOS, each thread of execution is again called a task. So these tasks, as you will see, are kind of independent programs, if you think of them as such. So what is the task management mechanism? So here we see effectively two kinds of possibilities. Either a thread is running or it is not running. And the idea is that you can be either in a ready state, meaning, okay, as a task, you're ready to start running if the scheduler allows me to do so. But a task can also suspend itself, and it gets in a suspend queue, or some resource is blocked, peripheral is blocked, so it will actually be context switched out and gets into the blocked queue. And of course, those blocked events can get into the ready queue as soon as that is possible, or they may get into a suspend state and so forth. So effectively, it's a slightly different setup as what we've talked about before. Before, we just had running, ready, and blocked, but now we have essentially split up the blocked into two kinds, suspend and blocked, if you will. So, and that can help you to make decisions as a scheduler, that little bit of refinement. Alright, so the task management mechanism, well, we can think of all the tasks having a certain priority. So for example, we have a task 1 and task 2 of some priorities n and n+1. The kernel gets the highest priority, 0, is always going to be overruling anyone else. In particular, when the RTOS tick happens, it will execute effectively a context switch if needed, maintains the queues, and so on. So that's what's happening at a higher level. So let's have a look at memory management. So FreeRTOS actually allows an unlimited number of tasks to be executed, so that's pretty cool, but of course only as long as resources are sufficient for that. So in particular, memory needs to handle that, and of course also just plainly the CPU time. I mean, otherwise you get very small little slices of compute time for each task, and the whole system that you intended to have may not work as required. Now, FreeRTOS is able to handle both cyclic and acyclic tasks. It allocates the RAM each time a task or a kernel object is created, so we have a special create function that we'll talk about shortly. And here we see that there are sections allocated to a task or an object. That section we call the stack in this particular case. And the size of the stack is configurable at task creation, so you can set configuration parameters. And the stack actually contains both what we call a task file and a task control board, and it allows simply the kernel to handle the context switching etc. Now, and all of this is being stored in what we call the heap. And there are a couple of choices for how the heap is maintaining its memory. So you can choose among those 4 possibilities. And heap 1 is, say, the simplest implementation, does not permit memory to be freed once it has been allocated. Heap 2, it's not like scheme 1, but it does allow blocks to be freed. And it does not, however, combine adjacent free blocks into a single large block, things like that. So you can have better management if you want to. Heap 3 is really a simple wrapper for the standard C library, malloc and free functions. So that means that you really want to make sure that malloc and free functions will be thread safe, or in other words, those threads separately do not conflict with one another when it comes to memory allocation. And heap 4 is a little bit different. It uses the first fit algorithm, and it combines actually adjacent free memory blocks into single large blocks. So for 1, 2 and 4 you need to actually set in the configuration file what the total heap size is that you would like to allocate for all those tasks that you are having, that you want to send, that you want to write your system on. All right, so that's about memory management, and that also brings us to kernel configuration. So when you look in the directory with the FreeRTOS, you will actually have, you can download FreeRTOS yourself, of course, from the internet, but we also have it in the shared directory. And in there you will also find, a document that describes FreeRTOS. And in there is this particular table that shows that this header file, FreeRTOS config, allows you to set all kinds of parameters. For example, you definitely want to make sure that you define the CPU clock properly, the tick frequency properly. There is something about the minimal stack size, the total heap size that we just talked about, and a bunch of other things that I also do not really know what they're actually about. So here we have the config use preemption. So it uses the preemptive RTOS scheduler, and that is kind of interesting because in the task that we have for you, you would like to use preemption. So anyway, the parameters actually continue. So we have a bunch more. As you can see, you can enable certain kinds of functions that you may want to use in your program, like multiple exclusion support functions. Here we have something with semaphores, so you want to be able maybe to use those, and other kinds of things. So it's quite flexible. You can indicate what you want, what you need, and with that write your own system. So you can write your tasks in such a way that you are going to lock whatever shared variable you have with another task and so forth. Okay, so now what about these task priorities? So how does FreeRTOS do this? Well, you can set a parameter that talks about the maximum number of priorities that you will have. So called max priorities. So for example, if you have 5, then you would have 0, 1, 2, 3 and 4. Actually 0 here indicates the lowest priority, and then 4 the highest priority here. Then the FreeRTOS uses a ready list to keep track of all these tasks that are currently ready to run. So if you're looking at that, here it is, at that statement, there's a list of lists. So let's have, there is a an array that for each priority level has as entry a list. And that list enumerates all the tasks that have that same priority. So I can have multiple priority 0 tasks, multiple priority 1 tasks, and so forth. So that's what's described over here. Now, so how is everything maintained? So first of all, let's talk a little bit about the system and tick frequency. That's important. You have these two parameters that you need to set appropriately. So it's described how you do that over here for your own MCU. And well, so effectively you just need to assign that in the proper way. Usually the tick is being set in the millisecond range. That's probably what you will be playing with. And so every time the tick interrupt fires, as explained in the last lecture, a whole bunch of things is happening. But in FreeRTOS it is it's coded up in a couple of different functions. So here we have the task switch context function that will be called, and it actually is going to find the highest priority ready task, and there may be multiple of those, and it will then actually cycle through those by assigning equal time slices for those highest priority ready tasks. So that's what's happening over here. And that leads to the core of FreeRTOS, which is effectively this piece of code, where what happens here is that you have this while loop, as you can see. I hope you can see that. And the while loop is also described over here. It effectively looks whether in that array of lists, which highest priority list, if you will, right, is not empty. Once you find it, you know which tasks you would like to start executing, which are those in that particular list. So effectively, the while loop starts at the priority level. That's the top ready priority, and walks down. That's the variable that you have, and then it decrements it until you find the highest priority level that actually has ready tasks. So all the other ones above it with high priorities, all those lists are empty and have no ready tasks to execute. So now this function over here, it's described over here, now grabs the next ready task from that priority level's ready list. And the idea is that we are going to cycle through those ready tasks. So here we talk about the next ready task, because you have a list and it has maybe 5 ready tasks, and you've already started executing the first and the second. So now it points at the third, that's the next one, and then the fourth, and then the fifth. Then it cycles back to the first, 2, 3, 4, 5 in that particular list. So that's effectively what's happening. And yeah, so does the context switch and everything that we talked about before. So here's an example. So for example, here we have that in the PX ready task lists we have, say, 3 priorities, 0, 1 and 2. And here you see that there's exactly 1 task in the list that contains all the tasks of priority 0 that are ready. There's nothing ready for, because it's empty, for task 1 lists, for priority 1 tasks. And for priority 2 tasks, there are a bunch that are ready. Task B, task C, and task D. You see the pointer structure of a list, right, with pointers. And effectively, so if we run through that while loop, we would obviously, well, this is the lowest priority, right, in our setup now. This is the highest priority. So you will notice that, oh, this is not empty, and say the pointer to the next task in that priority, in that list to be executed, points maybe a task at this particular one. So okay, so then you execute task C, and you move this pointer to this one, because then the next time you will look at this list, you want to execute task D, and then you circle back, and so on. So that's what you do. So that's what FreeRTOS is doing. So now what about the tasks? They're actually implemented as C functions in the following format. That's how you need to write them out. So it's a void, some, whatever you call it, task function, and you just need to put this in. That's just fixed. And the idea is that that task is actually a small program, just as if you had programmed it the way you have programmed it in, say, the basic MCU class. So the small program is literally has an entry point. Of course, you do your declarations of variables and all that kind of stuff, and you have an infinite while loop, like in the main program that we usually have. So it's an infinite while loop, and in that while loop I may call other procedures or whatever. That is of course possible as well. So you keep on, but you effectively execute this code forever in an infinite loop. Does not exit. And then so this particular task should not contain any return statement, because the idea is that you run through that code all the time, so you do not suddenly stop and return and get out of this task. That would be a problem. So no return statement, must not be allowed to execute past the end of the function. Again, it's the same thing, because then you would return as well, so you should not return out of the task. And if a task is no longer required, it should be explicitly deleted. That you can of course still do. Well, you use this to effectively create any number of tasks that you like to use. And each created task is now a separate execution instance with its own stack and its own copy of any automatic variables defined within the task itself. And you still, of course, have your global variables too, so you can do sharing, right? So that's effectively how it works. So you can still have this inter-task communication that we talked about, and so you may still need to do the proper locking and all that kind of stuff if you do that. Now, the task that we will ask you to do is not going into that depth, but we like you to merely be able to get FreeRTOS to work on your MCU. So, if you are looking at the function that creates a task, you'll see this particular, we will use the following type that contains a number of fields. And let's talk about each of those fields that effectively create a object of this type. So that object will have a certain number of fields that we need to know in order to handle that task, that the RTOS needs to know. So first of all, a pointer to that function, so which is just a function name that implements the tasks. Yeah, I need to know, of course, where I need to look at. There's a descriptive name that you can add in. It's not used by FreeRTOS, but you can use it as a debugging aid. And in the config file, you need to set the maximum number of characters that you can use for such a name. And then you can accordingly write names. So that is the PC name. We have the stack depth. And so each task has its own unique stack that is allowed by the kernel to the task when the task is created. So effectively specifies the number of words the task can hold. Depends a bit on your MCU, of course. So here is an example for Cortex with 32 bits wide and so forth. So you can calculate how much size you will allocate for the stack. The size of the stack used by the idle task is defined by some minimal stack size. It's adjustable. And then PV parameters, the value assigned to PV parameters will be the values passed into the task. So there are some parameters that you may want to give into the task. So you can do that. There's the priority. So it's effectively defining the priority at which you will be executing. And so we go from low to high, and that's what we've been talking about before. So so let's have a look at how tasks are created then. So effectively, when you do a PX created task, then it passes out a handle to the created task. And that can also be used to refer to the created task that you have created now in any other piece of the program, really. And for example, you can then change the task priority if you wanted to. I mean, you can do some own management of those priorities as well if you wanted to. But of course, FreeRTOS is really built for static priorities and so forth. But you can still get into the mode of using preemptive context switches, and you of course can read about that, and that will allow you to do priority inheritance and that kind of stuff. So there are two possible return values when you create a task. The first one is that the task has been created successfully, but it can also be an error, which indicates there's not sufficient heap memory if you get this error. So you really need to allocate enough RAM to hold this stack, this task data structures and the stack together. So that's something that can happen. So it's a limitation, memory limitation to what you can do. Now let's talk about the assignment that we have. So we talked about the first assignment last time, which is about this sort of, well, it's like a very simple RTOS that we modified a little bit, and where you will get experience if you look through the code with the complexity and how all of that works together. And you will play with some schedules. But this task is really about this open source FreeRTOS that is really used widely. So you can get it from this link. It's also in the directory, as I said, but what you need to do is you want to make it ready for your own MCU. So the source code comes with an official port to Atmega 323, but you do not have an Atmega 323, you have a 328. So what you need to do is you need to modify it. So how do you modify it? So one hint here, the timer configuration for the system tick needs to be modified. So and you may also need to change some configurations in this configuration header file. So you need to look that through and find out. And then why don't you modify the main code so that because you want to demo, that's the task, that's the assignment, to preemptively to create two preemptively scheduled tasks that cycle LEDs on port C and D. Something super simple like that, just to demonstrate how it works. Now that's the task. So it's a stand-alone assignment, in a sense not related to the final project. But having said that, if you can get FreeRTOS to work, right, it would of course be very cool to find out how you can make use of it in your final project. That would be of course yet another bunch of time that you will need to get that going, but you will again learn a lot from it. So it's really up to you how much you want to take out of this assignment and how much more experience you would like to gain for yourself. But you know, with MCU programming and everything that comes around it, the more practice, the more experienced, and it's really like the number of hours that you put into it, the more valuable you will become, because your expertise gets more and more and more. Which also means that you really need to have fun with it. If you don't have enough fun with it, then obviously you will not be able to put in more and more and more practice. So the idea is that this course, and the previous course of course, but this course gives you a few more handles to the broadness of what you can do with MCUs and embedded system design in general. But obviously you can go really far with this, and if you would say, do a summer internship somewhere where you would do something with an embedded system in a team, that would be the best, because then they can teach you a whole bunch of tricks and stuff like that. They may even not use FreeRTOS, they may have their own real-time operating system. That often happens, so you need to learn how that works. But you've now then studied 2 already, so then you get a real handle on how to use it. Because when you build a system, you will have shared resources. You need to go more advanced than this. You need to implement your own logs and all of that. But if it's a very simple system, say for a senior design project, then you would just maybe get away with even no real-time operating system, or for this final project, right? So that's pretty cool stuff. So any questions about this stuff? No? All right, let's finish.